Corporate boardrooms often treat intelligent systems as the latest iteration of enterprise software, a faster, cheaper way to process information and trim payroll. They look at artificial intelligence and see a high-tech labor-saving device. That perspective misreads the history of industrial transitions. The first era of automation, mechanization, replaced physical force. We used engines and turbines to substitute human and animal muscle, scaling up raw output. Later, mass production and the assembly line forced human effort to synchronize with the strict, repetitive rhythm of those machines. Management gained authority because coordinating that rhythm efficiently became more valuable than individual craftsmanship. The introduction of digital computing shifted the bottleneck from physical muscle to information storage and basic arithmetic, but these systems remained rule-bound. They executed predefined instructions on structured data, completely reliant on human operators to handle exceptions and make actual choices. Machine learning and predictive analytics move into a different domain. These systems identify patterns, estimate likely outcomes, and rank options, effectively automating perception, inference, and the act of selection itself. Treating programmable judgment as a simple efficiency tool obscures a massive relocation of authority. This transition shifts the power to decide what gets produced, who gets hired, and where capital flows. Historically, a firm's growth was capped by physical realities and the sheer volume of human clerical capacity required to coordinate information. Scaling meant hiring armies of clerks and middle managers to push paper, reconcile ledgers, and relay messages across departments. Early enterprise software digitized those archives, moving records into databases and accelerating reporting cycles. But the operational limit remained human. A manager still had to read the report, interpret the variance, and choose what to do next. Modern intelligent architectures absorb that connective tissue entirely. A predictive system can automatically flag an anomaly on a production line, route an approval, or dynamically adjust the pricing of a commercial risk in milliseconds, completely bypassing the human relay layer. When an organization transitions from automating physical execution to automating the choices that guide execution, the core laws of scalability change. The capacity to generate wealth is no longer tied to how many people you can organize, but to how many decisions your systems can optimize simultaneously. This diagram shows the classical model of political economy, which operates on a familiar duality. Capital provides the physical tools, the factories, and the financial backing. Labor provides the effort, the skill, and the direct coordination required to operate those tools. That bilateral relationship is breaking down. A third, active intermediary now sits between the owner and the worker. Code. It acts as a semi-permeable filter, severing the direct line of human management. This programmable layer dictates the operational rhythm. Workflow engines sequence the tasks, optimization algorithms determine the schedules, and live dashboards continuously evaluate worker performance against system-defined metrics. This structure splits the workforce in two directions. One small group moves above the code, designing the system parameters, setting the optimization targets, and governing the models. The majority moves below it, operating inside strict procedural boundaries to handle the physical and social exceptions the machine cannot resolve. Code, in this context, is an active organizing force. It dictates the practical limits of human discretion on the factory floor, in the warehouse, and in the white-collar office. If code is the new intermediary governing production, what fuels it? Strategic dominance in this era relies on three interconnected assets. The first is data. Information about transactions, behavioral traces, and environmental sensors forms the raw material. But stockpiling vast amounts of unstructured records is economically inert. Raw data only generates value when it is actively processed and linked directly to a decision point. That conversion requires the second asset, computational capacity. Compute is the modern productive ceiling. The ability to train large models, run high-volume inference, and process complex simulations dictates how quickly a firm can test assumptions and deploy outputs into live workflows. The third and most critical asset is control. This is the apex layer resting on top of the technical infrastructure. It encompasses the governance mechanisms, the optimization targets, and the architectural permissions. A robust data pipeline and massive compute clusters are useless if the system optimizes for the wrong metric. The control layer determines whose priorities the system actually executes, what margin of error is tolerable in a live environment, and precisely who holds the legal and technical right to override the machine. Strategic dominance no longer stems from owning a factory. It comes from owning and defending this exact architectural stack, because this is the mechanism that converts ambient information into enforceable economic action. This graph illustrates the cost structure of a traditional firm. As output and scale increase along the bottom axis, the variable costs, wages, middle management, and coordination burdens rise steeply in tandem. More revenue requires proportionately more human effort. An automated firm carries a completely different profile. It absorbs massive, upfront fixed costs to build the intelligent core, including capitalized software development, systems integration, and extensive cloud architecture. But once that infrastructure is deployed and stabilizing at scale, the cost to process an additional unit of activity, whether that is a loan approval, a logistics routing change, or a customer service interaction, drops rapidly, approaching zero. We call this expanding gap operational asymmetry. As the system handles higher transaction volumes, the cost curve remains flat, while the revenue line climbs steeply, separating the growth of the firm from the growth of its headcount. This structure also aggressively shrinks hidden operational leakage. Instead of paying human workers to correct downstream rework, untracked exceptions, and duplication errors, the standardized automated system prevents those defects upstream. Consequently, the math of business survival shifts. Automated firms require massive scale and transaction volume just to break even on their heady initial investments. But once they cross that threshold, their margins expand at a rate traditional firms simply cannot match. This mathematical decoupling of revenue generation from proportional human labor is the true engine of wealth accumulation in the intelligent economy. It allows capital to scale without pulling labor along with it. In a machine-led economy, scale takes on a new meaning. In the industrial era, scale lowered the cost per unit. Today, reaching massive scale actively improves the quality of the firm's judgment. This diagram maps the continuous feedback loop driving modern monopolies. It begins with user volume. A larger base of active users generates a massive continuous stream of behavioral traces and transactional data. This rich, proprietary data is not just stored, it is fed directly back into the computational layer to refine and update the system's predictive models in near real time. Those highly refined models then output superior risk pricing, tighter inventory forecasting, and sharper personalization. That improved performance attracts an even larger user base, pulling in more capital and starting the cycle over again. This compounding learning effect creates insurmountable structural barriers to entry. A smaller rival cannot simply borrow enough capital to build a competing model because they lack the years of accumulated edge cases and user interactions required to train it. Market concentration becomes inevitable under these physics. The system that observes the most human behavior learns the fastest, effectively cornering the market on high-quality economic decisions. As this architecture takes hold, practical authority relocates. Middle managers whose primary value was relaying information are bypassed. Frontline professionals find their independent discretion narrowed by algorithmic scores, and workers are increasingly subjected to the continuous, unblinking supervision of automated metrics. Power heavily concentrates upward and inward. It flows to the system architects who write the rules, the entities controlling the computational infrastructure, and the executives who gain centralized visibility without the delay and fog of human reporting lines. Automated systems do not remove corporate politics or bias, they simply push them upstream. Value choices are quietly embedded in the selection of training datasets, the design of optimization targets, and the mathematical definitions of acceptable risk. While public debate remains fixed on job replacement, the structural reality is more focused. Control over the architecture of choice is the decisive factor for future economic power. Economic leverage, the distribution of wealth, and the pathways for social mobility in the coming decades will belong exclusively to those who govern the machinery of automated judgment.